Hello everyone, Integrals 2, day number 1, short chapter here on applications of integrals. We're going to start with some kinematics revisited. So day 1 and day 2 will be kinematics related. Let's start here with the fundamental theorem of calculus, part 1. As you look at this first equation, you can see that this is the fundamental theorem of calculus, part 1, provided that the derivative of big f of x is equal to little f of x. Now this applies directly to the idea of position, velocity, and acceleration. So for example, the integral from a to b of the velocity is equivalent to the position at time b minus the position at time a. So in essence, what this is this is the change in position. Change in position. Okay, if I wanted the change in velocity from time A to B, I would take the integral from A to B of the acceleration. And of course, that would come out to be the velocity at time B minus the velocity at time A. So now really what I've got is I've got an equation that I can solve for any one of those three, provided I have the information necessary to have the other two. Okay, let's look at and talk a little bit about the schematics involved in position, velocity, and acceleration. So how are position, velocity, and acceleration related? Well, we know that position, s of t, which at times can be referred to as x of t, is position with respect to time. So velocity is the derivative of position, or the change in position, whereas acceleration is the change in velocity, which is equivalent to the second derivative or concavity of the position function. Okay, so how do we know if a particle is moving to the right? Well, we know a particle is moving to the right if v of t is greater than 0, or how about to the left? What if then v of t would be less than 0? At rest, v of t is equal to 0. And there's one I haven't put on here, but how about changing directions? Let's change direction. Okay, so the change in direction happens when v of t equals 0 and changes sign. Changes sign. Okay, so beware, there's a big difference between at rest and changing direction. How do we know if a particle is speeding up? Well, a particle is speeding up if v of t and a of t are the same sign, and a particle is slowing down if v of t and a of t are opposite signs. Okay, very good. Those are just some basics of kinematics, but we want to get into a little bit more with distance and displacement and move on to some word problems here. So, okay, so what is the difference between distance and displacement? All right, so let's say here's my house. It's a nice house. It's got a window. Okay, there's no door because you have to climb to get into it. You got to get a workout when you can. All right, and here's school. And it's a really awesome building. It's got a flag on the top. Yep, school. And I'm walking to school, and the distance from home to school, let's say, is, I don't know, 2 miles. All right. And as I go to school, I'm walking to school. Oh no, I forgot something. I start walking back. Oh, wait a minute. No, it's in my backpack. All right. I got to school. All right, this dotted space, time I was traveling back toward my house, counts only toward total distance traveled, right? Or distance. Whereas displacement is 2 miles regardless. So my displacement in this scenario is equal to 2 miles. Well, I don't know my distance until I know how much I backtracked. Let's say I backtracked 3/4 of a mile. Okay, so that distance is 3/4 of a mile. So then what would my total distance be? Well, the total distance traveled, let me change colors here. Total distance traveled, well, I would need to know something here. Let's say we turned around at the halfway mark at 1 mile. Well, it would be the 1 mile I traveled while heading to the right, plus the absolute value. Now, we would consider this -3/4 with regard to distance because it's not traveling towards school. So we take the absolute value of that, and then we'd add the rest of the portion of the graph. So as I travel 3/4 of a mile to the left, that leaves me at 1/4 of a mile from my home, which means I have to then travel 1 3/4 miles now to school. So that's 1 3/4 of a mile to school. So our total distance traveled would equal 1 plus 3/4 plus, I'm going to call this 1 3/4. What would that be? 7/4. Okay, so that'd be 10/4 and 4/4, which would be 14/4, which would be 7/2 of a mile. We had to go 7/2 of a mile because we thought we forgot our protein mixer. Okay, so within the context of a graph, let's see what that looks like. So let's put this, let's put v of t up here and consider our situation here. Well, let's say we traveled 1 mile, and then 3/4 of a mile, and then what did we end up being? 1 3/4 of a mile. All right, does that look familiar? Absolutely it does. Therefore, we can see that we would consider the green portion of the graph as distance moving to the left. Any red portion of the graph, the area under the curve, would be the distance moving to the right. Therefore, I can write displacement will equal the integral from 0 to, let's say, I don't know, let's say it took 30 minutes, right? 0 to 30 of my velocity graph with respect to time. Whereas total distance, I'm now considering the absolute value of that green space. So in essence, what I'm doing is I'm then considering that a positive area, because I want to know the total distance traveled. So I would go with the integral from 0 to 30 of the absolute value of the velocity. All right, that's the difference between displacement and distance. All right, let's look at how that applies to a few situations. Okay, given the velocity function below, t squared minus 8 over t plus 1 squared, find the displacement and total distance traveled by the particle from 0 to 5. Calculator is good to go on this one, obviously. With a function like that, we probably wouldn't put you through the pain and hassle unless we didn't like you. So here we go. What I do first is in y1 on my calculator, I'm going to type x squared minus 8 over x plus 1 squared. All right, that's going to be helpful, obviously. Do that. If you have a different version calculator, just talk to me on the side and I'll help you with that. Okay, now I press math 9. Math 9, okay? The math button is like right here under the alpha button. And then press option 9. That'll bring up this notation if you have a newer calculator. Okay, so now with that notation, I want to go from 0 to 5 of a function. Well, that function I'm going to use is y1 with respect to x. Okay, and I can pull up y1 relatively quickly by pressing alpha trace. Alpha trace will get you this screen, and then just press enter on the function that you want. Okay, now I use, for absolute value, press the math button and then scroll over to the number option. The first option is abs. That will give you the absolute value of that function on that interval. Okay, so when we talked about the difference between displacement and total distance traveled, we took the absolute value when we wanted the total distance traveled. So this integral right here is 0 to 5 of the absolute value of y1 with respect to x. This is our total distance traveled, and this here is our displacement. Displacement is the change in position from time 0 to time 5. We can find the change in position. We just don't know where necessarily the position started. Okay, now this would be the total distance traveled throughout. So it looks like whoever this was, if they were walking to school or to the gym, they had to backtrack a little bit and then take off and head again. Okay, let's look at example 2. Example 2 says find the equations for the position and velocity of a particle that maintains a constant acceleration of negative 32 feet per second Now this may look familiar to you physics students, but let's work this out and maybe it'll start to show you a little bit more. Okay, so A of t is equal to negative 32. Now V of t is equal to the integral of A of t with respect to t. So the integral of negative 32 with respect to t is negative 32t plus whatever the initial velocity would have been. Okay, so plus c. Now, you might be saying, well, how do you know it's the initial velocity? Well, here's why. Because negative 32t plus c, well, I want to find c, so what is v of 0? Well, v of 0 would equal negative 32 times 0 plus c. So c has to equal v of 0, or what we'd call the initial velocity. Okay, now the position, I'm going to go with s of t, is equal to the integral of v of t dt. Therefore, the position is equal to the integral of negative 32t plus v0 dt, which will be negative 16t squared plus v sub 0 t plus, and for the same reason, the initial position. Now this should look very familiar to all you physics students out there. If you're not a physics student, well, deal with it and we'll talk about it later. All right, let's move on and look at an application of that. All right, so given that a particle moves with an acceleration of a of t, find the position and velocity functions for the particle if s of 0 is 40 and v of 0 is 60. So again, v of t will equal the integral of a of t. So v of t is, that would be 5t squared plus v sub 0. So v of t will equal 5t squared plus 60. All right, there's our velocity function. Now s of t, or our position, will be equal to the integral of v of t dt. So the position at any time t will be equal to the integral of 5t squared plus 60 dt, which will be, that'll be 5 over 3t cubed plus 60t plus the initial position, which is 40. Now we could find the position of the particle, given that we only know its acceleration and initial position at any time, as well as the velocity at any time. Okay, let's continue. Number 4, the function v of t in meters per second of a particle moving along the x-axis is given. Use analytical methods to solve. Okay, so analytical methods are algebraic. They are not calculator related. So I did put an image of the calculator here, and I'm going to do that in a moment just to show you why my explanation is what it is. So I'm going to, let's see here, we want to solve, determine when the particle is moving to the right, to the left, and at rest. So that means I want to know when v of t equals 0. All right, so when does v of t equal 0? My Apple Pencil is not working. Hold on. Yes, it is. I was on the wrong little thing there. I was on the little hand that moves it instead of the pen. Okay, so when is v of t equal to 0? Well, t over 1 plus t squared, when does that equal to 0? Well, that would be only when t equals 0. Now, think about this for a minute. As t goes to infinity, what does t over 1 plus t squared go to? Well, it goes to 0. It never gets there, though. So v of t actually never equals 0, except at 0. All right, so the particle is at rest. Particle is resting when t equals 0. Particle is moving to the left like never, right? Because v of t, apparently, according to the graph, is always going to be positive. Plus, I could see that analytically. If I were to plug in positive numbers, I'd just get positive outputs. It's moving to the right when t is greater than 0. Okay, so we want to find the particle's final position, s of 3, if the initial position is 4. Okay, so what I want to do to find the position s of 3 is I want to take the integral from 0 to 3 of v of t. Okay, that'll equal s of 3 minus s of 0. So s of 3 will equal s of 0 plus that change in position. Okay, so I'm going to do a little work. I'm going to find this s of 3 by taking s of 0, which is 4, plus the integral from 0 to 3 of v of t. I'm very tempted to use my calculator to do all the work for me, but that wouldn't be doing it any justice since I said analytically only. So I'm going to integrate, let's find the integral of t over 1 plus t squared dt. Let's use a u sub, so 1 plus t squared, so du is equal to 2t dt, so 1/2 du is equal to t dt. Okay, so then this is equal to 1/2, the integral is equal to 1/2 1 over u du, which is equal to 1/2 ln of u. Therefore, I'm going to plug back in for u, 1 plus t squared. So this would equal 1/2 ln of 1 plus t squared evaluated from 0 to 3. So the position at time t equals 3 will be 4 plus 1/2 times the natural log of 10 minus the natural log of 1. Okay, and we know the natural log of 1 is 0. So the position at time t equals 3 will be 4 plus 1/2 the natural log of 10. Oof, I don't know what that is, but it's goofy. Now, it may, in some cases, ask you to write this in the form a plus ln of b to the c power, let's say. I'm making this up to some extent. But if I wanted that in this form, or r's in that form, I would bring the 1/2 up as a power, and that would be our answer. So we could identify a, b, and c as 4, 10, and a half. Okay, let's continue on with another example. Okay, here we have a somewhat of a word problem using a piecewise function. Part A says graph the velocity for 0 to 70. When is the velocity at max? So velocity max, we'll write over here. And velocity is 0. And let's sketch the graph up here. Okay, so it looks like the piecewise function is linear in all cases on the 3 stems. So let's go out 20, and then we'll go to 45, and then it wants us to go out to 70, so that would be about right. 70. Okay. So the velocity is 3 times the time from 0 to 20. So 3 times 20 is 60. That's nice because that'll match up. So the velocity follows this linear pattern from time 0 to 20. And then it is 60 from 20 to 45. And then it looks like it's 240 minus 4t from 45 on. Okay, so let's find where that would equal 0. So where would 240 minus 4t equal 0? That would be when t equals 60. So here at 60, it's going to equal 0. Therefore, at 70, 240 minus 4 times 70, that'll be negative 40. So I'll have an output here of negative 40. So there's my velocity function from 0 to 70. Let's note that this point is the point 70, negative 40. Okay. When is the velocity a maximum? Well, the velocity is maximized at 60 from 20 to 45. So when t is between 20 and 45, the velocity is maxed out. When is it 0? It's 0 at t equals 60. Okay, so t equals 60 is a point when, whatever this is, a car changes direction, right? Because it goes from positive to 0 to negative velocity. Okay, let's look at part B. It says, what is the distance traveled by the automobile in the first 30 seconds? Well, the distance traveled would equal the absolute value of the velocity function from 0 to 30. Okay, now in this case, if you look at the graph, the velocity is positive on all values from 0 to 30, so I won't necessarily need the absolute value, but it's useful to think of it that way. That'll equal, and we can look at this geometrically. I'm just going to find the area under the curve. So the area under the curve from 0 to 20 is going to be 1/2 of 20 times 60, which will be 600, plus the area of this rectangle right here. So our first area was here, 600. Our second area will also be 600. It'll be 10 times 60. So the distance traveled in the first 30 seconds looks to be 1,200 meters. Okay. How about the distance traveled by the automobile in the first 60 seconds? Well, let's look at part C. So the distance traveled in the first 60 seconds. Again, I would visualize using the absolute value of v of t, even though velocity will be positive on the entire interval. Therefore, that will be the position at time 60 minus the position at time 0, which is kind of irrelevant here because I don't want to work piecewise with those functions. I'm just going to work geometrically. So that will be the integral from 0 to 30 of v of t plus the integral from 30 to 60 of v of t. All right, so I knew the first part was 1,200 meters. The second part, I'm going to find each of these areas separately. So 15 times 60. 15 times 60 is 900. And then 1/2 of 15 times 60 is 450. So I'm going to have 1,350 acquired, that much distance acquired from time t equals 30 to time t equals 60. So it looks like the total distance traveled in those first 60 seconds is 2,550 meters. All right, let's look at part D. What is the position of the automobile at time t equals 75? Okay, that's not very nice because we only went out to 70. So where would our function be at 75? I think it would be, if I plug in a 75, it's going to be at negative 60 for its velocity. Okay, so I'm going to find position. That means I'm going to take the integral from 0 to 75 of v of t, that'll equal the position at 75 minus the position at 0. Okay, let's figure out what this will be. So position at 75 is equal to initial position plus change in position. Now you always want displacement when it comes to change in position. So just because the velocity goes below 0, we still want displacement for change in position. Okay, does it tell us what our initial position is? Yeah, I mean, contextually, a vehicle that starts somewhere just starts at that point. So we're going to consider s of 0 equal to 0. The integral from 0 to 75 would be the integral from 0 to 60, which we already know, minus, because it'll be a negative area, or I could put plus and then just make sure I know it's a negative area, from 60 to 75. Okay, so the position after 75 seconds will be, we had 2,550 meters traveled, minus the 450 meters traveled the other direction. Therefore, for part D, the position after 75 seconds would be 2,100 meters from wherever they started. All right, there you go. Let's continue on with a couple more examples, and that'll be it for today's lesson. Okay, number 6, the graph of v of t is given below, where the initial position is 2. All right, so we want to find where the particle is at the end of the trip. We want to know its displacement. Okay, so displacement is related to location. All right, so we're going to take the integral from 0 to 5 seconds of v of t, which will be equal to the position at 5 minus the position at the start. We know the position at the start was 2, so I'm going to rewrite position at time 5 is equivalent to the position at time 0 plus the change. And again, this is displacement, so I'm going to consider any area below the x-axis as negative. So the position at 5 will be the initial position plus the accumulated areas. Okay, so let's talk about them. Well, this area, this first triangle, that'll be an area of 1. This rectangle will be an area of 4. This triangle will be an area of 1. And this triangle will be an area of -1. Therefore, the position at time 5 will be 2 plus, it looks like 5, which is 7. Now, notice that the change in position was 5 units. That's the displacement. So the displacement is 5 units from where it started. All right, let's look at finding the total distance. So the total distance traveled by the particle will be the absolute value of v of t. And I'll just take all these areas and accumulate them, taking the absolute value of each. Now the ones that are already positive, I don't care to do that to. But the one that is negative, I will do the absolute value of. So total distance traveled ends up being, looks like 7 units. So it looks like a backtrack, right? A backtrack of 1 unit. So total distance traveled, 7 units. We could look at this schematically. We know that time 0, we're at position 2. It looks at time 4, so at time 0, we're at position 2. We move to the right until time 4, where, oh boy, what would that be? We'd be at position, let's see, 6. Let's see, S of 4 would have accumulated, 6 units. So that'd be at 8. So the particle is moving to the right for 4 seconds. It stops, and then it moves back for 1 second. and then it stops. And where does it stop? It stops at 7. So here is the displacement. Displacement right here, which was 5 units, and total distance, which was 7 units. All right, there you go. Let's look at one more example. Let's have at it. All right, this is a no calculator problem. It is a word problem, which will require your knowledge on pretty much everything we've done so far. So let's get it started. Let's see. For 0 to 12, a particle moves along the x-axis. The velocity of the particle is given there. The particle's position at time t equals 0 is -2. So x of 0 equals -2. Part A, it says, when is the particle moving to the left? Well, the particle will move to the left when v of t is less than 0. Let's find where v of t is equal to 0 and do a little sign analysis. Okay, so cosine of pi over 6t is equal to 0. When is the cosine equal to 0? Well, the cosine is equal to 0 when pi over 6 here is equal to either pi over 2. So I'm taking the angle, setting it equal to pi over 2 because cosine is 0 at pi over 2. I'm also going to say that that is true when pi over 6t, or the angle, is equal to 3 pi over 2. And I'm going to actually go out one more, just in case, because I don't know how this interval will apply to 0 to 12. 5 pi over 2. So if I were to solve, that would mean that t, I'd multiply by 6 over pi, which would mean that t equals 3, v of t equals 0. So v of t equals 0 at t equals 3. Okay, where else? If I multiply by 6 over pi, I get 18 over 2, which is 9. Okay, t equals 9. And then this third one, it looks like I would get at t equals 30 over 2, which is 15. Now, I don't need that. This value is irrelevant to me. And the reason why is because it doesn't fall in that interval. So I know that v of t equals 0 at t equals 3 and t equals 9. So on the interval from 0 to 12, v of t equals 0 at 3 and at 9. Okay, so what does cosine look like? Positive cosine at 0 equals 1. So on this interval, it would be positive. Clearly, here it would be 0. Cosine oscillates, so it would be negative, and then 0, and then positive. Therefore, the particle is moving left on the interval where t is between 3 and 9. Okay, and that's because v of t is less than 0 on that interval. Okay, part B, write but do not evaluate an integral expression that gives the total distance traveled by the particle from t equals 0 to t equals 6. Total distance. So from 0 to 6, we're going to take the absolute value of v of t, dt. Done. That's it. Free point. That's very free. Okay, part C, find the acceleration of the particle at time t. Okay, so the acceleration of the particle will be equal to the derivative of the velocity. Okay, so acceleration then will be the derivative of cosine pi over 6t, which will be pi over 6 times negative sine of pi over 6t. So that is our acceleration. Now it says, is the speed of the particle increasing, decreasing, or neither at time t equals 4? Well, v of 4, as I can see from my graph up here, will be negative. So it'll be less than 0. Less than 0. Let's find a of 4. A of 4 is going to be negative pi over 6 sine of pi over 6 times 4, which is the same as 2 pi over 3. Okay, so sine of 2 pi over 3, this value is positive. Therefore, a of 4 would be negative. I don't even care what it is. But since v of 4 and a of 4 are the same sign, since v of 4 is less than 0 and a of 4 is less than 0, the speed is increasing. Okay, part D says find the position of the particle at time t equals 4. Okay, part D. Position of the particle, now I forgot, what does it say? Position of the particle at t equals 4. Okay, so I want to take the integral from 0 to 4 of v of t. Well, that's cosine pi over 6t dt. That'll give me the position at time t equals 4 minus the position at time t equals 0. I wonder if I know the initial position. Let's see. Yes, it gives me the initial position, x of 0. I should use x because it prompts me with that. X of 0 equals -2. Therefore, x of 4 will equal x of 0 plus the integral from 0 to 4 of cosine of pi over 6t dt. All right, so our position at time 4 will equal -2 plus the integral. Now, the integral of cosine pi over 6t is kind of weird, but it's 6 over pi sine of pi over 6t. Okay, so the derivative of that would be cosine of pi over 6t. And I'm going to evaluate that from 0 to 4. Okay, and only that, not the 2, right? So let's see what we get here. Evaluating that, I get x of 4 is equal to -2 plus, that'll be 6 over pi sine of 4 times pi over 6, which is 2 pi over 3, minus 6 over pi times 0, because the sine of 0 is 0. All right, so we can simplify this. If I'm not using a calculator, I would leave it in an exact form. That'd be 6 over pi times square root of 3 over 2. So that'd be 6 root 3 over 2 pi. There you have it. There's your position at time t equals 4. All right, guys, that's it for kinematics revisited, displacement, total distance, and all that good stuff. Okay, we'll see you in the next video.